Since we know an LNA is the first stage in a receive chain. So this LNA needs to have low noise and high gain. So both of these requirements are important to help in keeping the noise figure of entire receiver to be as low as possible. In addition to that, since it's the first stage, it also needs to maintain the matching as the signals are coming from outside the chip. While keeping these points in mind, we need to make sure when the LNA is designed, it is also stable. In addition, LNA should be able to handle out-of-band blockers which are attenuated by the band select filter. Even though attenuated by the band select filter, but still there can be significant power. So those out-of-band signals should also be processed by the LNA without causing any nonlinearity. So the linearity, stability are important. In addition to that, we have to make sure LNA meets the specification for the noise gain and the matching. So let us try to design an LNA using a simple common source amplifier, which all of us are already aware. To design common source amplifier to be used as an LNA. In the common source amplifier, just a MOSFET biased in saturation. And here I may not be showing all the biasing details. We can perform the small signal analysis to find the gain and the noise performance. Input is coming from source. And output is taken at the drain of the MOSFET. Since we are trying to design this amplifier, which will be also operating a few gigahertz frequency. So on the input side, we need to also include parasitic capacitance of this MOSFET. And in addition to that, since we are interested in the matching, we know that just by putting a capacitor may not be sufficient. So this may not be matched. So what we can do is we can also include the gate resistance of the MOSFET to provide some real impedance so as to see if it can be used for the purpose of matching. Detailed model of a MOSFET, find that has a gate resistance and a gate to source capacitance. VGS and now for this very simple circuit, let us try to see what is going to be the gain. So if we first find out this voltage VG, it is going to simplify in finding the V0. This voltage VG is going to be equal to, if this is Vs, you can just see a simple low pass behavior. It is going to be Vs divided by 1 plus S CGS Rs plus Rg. And this gate resistance, we'll see that will be of the order of a few ohms. Now we can find output, which is equal to minus GMRD multiplied by this Vg, and Vg in turn is equal to Vs divided by 1 plus S CGS Rs plus Rg. So here we have also ignored any capacitance at the output, even though that is a important detail. But here for our noise calculation, it turns out that it is not going to affect the conclusion. So here we see there is a pole at 1 by CGS Rs plus Rg. And if we are operating at gigahertz frequencies, so many times it is possible that this pole may be appearing much before the desired frequency, which can cause signal attenuation. Okay, so now let us try to find out what is the noise figure of such a simple common source amplifier. To do that, let me show the noise sources. So this Rs is going to add noise. Rg will also be adding its own noise. The MOSFET, you will have a drain noise and the Rd. So if we find the total output noise at the V0, it is going to be sum of the noise power of all the noise sources. So here, not just here, so in most of the cases, you might have already seen that whenever we have multiple noise sources, we will assume that all the noise sources are uncorrelated. So their noise power is going to get added. So the noise due to the Rs, which is 4kT Rs, is going to get multiplied by the same gain, whatever is we are seeing from the input to output. This gain is square, and this gain we know is VO by Vs, which is GMRD divided by 1 plus omega square CGS square Rs plus Rg. So this is 4kT Rs gain square plus the noise due to Rg, 4kT Rg, again gain square. We know that these capacitors don't add any noise. So next we need to talk about the noise contribution from the transistor. So ignoring the flicker noise, only talking about the thermal noise because we are talking about signal frequency of the order of gigahertz. So this is going to be 4kT gamma GM, and this current is going to flow through this impedance Rd to Rd square plus the noise due to Rd, which is nothing but 4kT Rd as it is. This is the total output noise PST, and if you want to find the noise figure, we need to also know the noise at the output due to the input, which is nothing but this first term. So I can write the noise factor as 1 plus 4kT Rg gain square plus 4kT gamma Gm Rd into Rd plus 4kT Rd divided by 4kT Rs into kT square. Now here I will start making some assumptions to simplify again our derivation. So if we look at all the three terms, we'll see that this 4kT Rd is appearing as it is, where this term here is having some GMRD getting multiplied with Rd. So this term will be again much more than 4kT Rd. And the first term also is having a gain square term. So if we compare these three terms, we will find that this 4kT Rd can be ignored compared to the other terms. For our discussion, we will ignore 4K TRD. We divide all these, both these terms with 4K TRS gain square. We get RG by RS plus gamma GM RD into RD divided by RS. And this gain square is GM square RD square divided by 1 plus omega square CGS square RS plus RG whole square. RD square gets cancelled. First, we will look at this term. Since we are operating at a high frequency, we will find that at those frequencies, this omega CGS RS plus RG will be much more than 1 because we will be operating way beyond the pole frequency of this low pass filter at the input. And such a scenario, again, we will ignore this one. Another approximation we can do is when we are adding this RS plus RG, this RG will be just few ohms and RS can be pretty high. So again, here we can, just to simplify the derivation, we can ignore RG when compared to RS. So including these two approximations, I can write it as RG by RS plus gamma. So here we get GM by RS multiplied by this omega square, the numerator. We have RS square, because RG has been ignored. So we have done two things. This as well as this. And if you simplify, then you get in the denominator GM by CGS whole square is 1 plus RG by RS plus gamma GM RS into omega square by this GM by CGS. And we can see that this GM by CGS will be having the dimensions of a frequency. I will define the GM by CGS as omega t. And this GM by CGS is a very important parameter for any MOSFET in a CMOS technology, because it tells you that for a given transconductance, how much this unwanted parasitics I'm going to get. The GM is the desired quantity from a MOSFET. CGS is undesired. And you want this term GM by CGS to be as high as possible. This is also called as transit frequency. And this is an important figure of merit for any process. And to find this transit frequency, a very simple test setup is used. So you bias the MOSFET in saturation and then try to find the current gain. So you apply an input, try to measure what is the I out, I in. MOSFET is biased in saturation, okay, with some transconductance GM. Here we are ignoring the CGD. And if we try to find the I out by I in, the current gain, see that this I in is going to flow to this capacitor, going to create a voltage, which is I in divided by SCGS. And this voltage is going to again create a current at the output. So this will be GM divided by SCGS. This is going to have again a 1 by F kind of profile with frequency. Your current gain, see this 0 dB. So the frequency at which this current gain becomes 0 dB is called as omega t. This is very easy to see from here. You can see that at omega t, this current gain becomes 1 and this frequency will be Gm by CGS. This is also called as transit frequency. And here it is in radians per second. You can as well find the Ft, which is Gm by 2 pi CGS. If we know the Ft, effectively we get an idea about till what frequency a MOSFET can be used for amplification, because beyond some frequency its current gain is becoming 0. It means that most of the signal will be attenuated at the gate itself. So it is always better to operate at frequencies which are much lower than the transit frequency. So a simple thumb rule is at least 5 to 10 times lower than Ft if you operate. Then it is easier to design a circuit. So this is the Ft or the omega t, which is coming into to picture this expression. Okay, so here, we have got this noise factor which depends on Rg, Rs, and of course the biasing of the transistor, along with this expression omega by omega t whole square. So as the frequency increases with respect to the omega t, we can again see that the noise factor is going to increase because we are seeing this kind of a low pass behavior at the gate side. So one interesting thing in this expression is we see Rs is coming in numerator as well as denominator. We should be able to find an optimum value of Rs at which this noise factor will be minimized. So by doing this simple first derivative of f with respect to Rs, let's see that it is G by R square gamma Gm square. If we equate it to 0, find that this Rs optimum is going to be equal to 3 by gamma Gm into omega t by omega. So there is an optimum source impedance at which we can see that the noise factor is minimized, and this minimum noise factor is equal to 1 plus. When it is minimized, you will find that both of these terms are equal. So it is going to be equal to 2 Rg by Rs opt, written as 1 plus 2 GMRg into omega by omega t. So there is a optimum Rs which minimizes F min depends on the minimum noise factor, depends on the. So in addition to the other factors, the ratio of omega with respect to the omega t. So if you are just operating, let's say, working in a process which has much higher omega t, so by default you can see that your minimum noise figure possible using this common source amplifier will reduce. So both of these points are really important. So this also gives rise to a concept of noise matching. Means when we are trying to find the looking at impedance from the source side, then it's not just about the matching with respect to the reflection. We also need to worry about what is the optimum source impedance, which is going to give rise to the minimum noise figure. The optimum value of RS for noise matching may not be same as for the power matching. This can be a problem in cases when we are trying to design a low noise amplifier where we have to meet the low noise performance along with good matching. So this is the discussion about using a common source amplifier to be used as an LNA, and already we can see multiple challenges. First of all, this gain is going to be reduced because of this low pass behavior at the input. Output pole anyway we have ignored, so output pole will also add to more reduction in the gain. In addition to that, there is a strong trade-off when trying to do the power matching along with the noise matching. There is another practical problem whenever we are using MOSFET as an amplifier. We'll see that any practical amplifier design will look like this, where the input is applied, the gate, and the output is taken at the drain. And the output impedance of such an amplifier can be pretty high because we will also be having some kind of active load on the drain side, and this active load will make sure the output impedance is increased to increase the overall voltage gain. And in addition to high R out, there will also be this load capacitance, which may already include the capacitance seen at the drain of this MOSFETs. So this R out combined with the CL will be giving a pole at much lower frequency, so that when we try to find or when we try to obtain the gain will be heavily attenuated. Here we are ignoring the input parasitics completely, just looking at the output parasitics. That itself, we can see that VO by V in frequency increases. We are going to see pole at very low frequency. Frequency is your 1 by CL R out, whereas we may be operating somewhere here. As a result of which, if we just take the standard the amplifier architecture we know, we are now never going to get appropriate gain at the output. So what is done is, since we are limited by this low pass behavior, this low pass response is shifted to a high frequency, so that if we are operating, let's say, at a higher frequency within this bandwidth, there won't be an attenuation because of this low pass behavior. To understand how this frequency response can be shifted to a higher frequency, let us look at the root cause of this attenuation. So this attenuation is happening because at high frequency, this current starts flowing into this capacitor, which will attenuate the output voltage. So what if we can compensate the current which is flowing in the capacitor? If that happens, then entire signal current will be flowing to the R out of this amplifier, and it will not flow to the CL. So it turns out that if you connect an inductor in parallel to the CL, then at the resonance frequency of parallel combination of LC, current supplied by the inductor is exactly equivalent to the current going to the capacitor, so that the net current seen towards this LC parallel combination will become 0, and that current will only flow to the real impedance of the out of the amplifier. This IL can supply IC at omega is equal to 1 by root over LCL. So this is the observation. Now this will happen exactly around this omega. So around this omega frequency, we can expect high output impedance, whereas the other frequencies will see low output impedance. Whereas without inductance, only at low frequency we could see high output impedance, and high frequency we are seeing attenuation because of CL. So the modified frequency response of the output impedance look like this kind of behavior, and this output impedance omega naught is equal to just the R out. This is also called as tuned load. Well, now we can tune the resonance frequency so that it is at the desired frequency of operation, so that we can get a higher gain. To further simplify this circuit, we can see that if this inductor is present, inductor itself can be used to provide the DC current for the MOSFET biasing, and we can get rid of this active load. Amplifier. Tuned amplifier is really important when we want to operate at high frequency. So in our desired frequency of operation, we can most of the time just replace this LC combination as some real impedance at omega naught and continue our analysis. We looked at the common source amplifier and we found that CSA is not suitable for LNA. First is it has high input impedance, mainly because we are looking at the gate. Also has a issue with the noise matching and the power matching. So one way to solve this input impedance problem is we can take a common source stage, and we know this Vs will be having a source resistance of Rs. So we can just add another resistance Rs for matching. We can then have a tuned load at the output, and yeah, so this looks like this matching problem is solved. But if we do the analysis, we will see that the noise contribution from the RS to the output is same as the noise contribution due to this matching ratio at the output. So even in the best case scenario, when the MOSFET noise we ignore, we'll find that the noise factor will be at least 2 because both of these components are going to be equal. This guy will be giving F greater than 2 or noise figure greater than 3 dB. So this is the minimum noise figure which we can achieve, and in general this noise figure will be much more than 3 dB because of MOSFET. Another way to reduce the input impedance of a common source amplifier is by using a shunt feedback at the input. Okay, so we know that if we want to reduce this looking at impedance, we can do a shunt feedback, and the simplest shunt feedback is just by connecting a feedback resistance from the drain to the gate. With this shunt feedback, again we can do a very simple analysis.